let's take a look at a more complicated type of situation. What happens when you launch an object upward, or it starts with some initial velocity going up? Well, we have to look at the motion of the object on the way up and on the way down. Now, since the object's initial motion is upward, we're going to call the up direction our positive y. We will call our acceleration, which points down, is in the opposite direction as our positive axis. So our acceleration now is going to be negative g, or negative 9.8 meters per second squared. Now, things to note here for objects that travel up and down. There are a couple tricks that make this much, much simpler. At the highest point, as an object goes up, right before it comes down, for an instant, its velocity is 0. So at its highest point, we know v equals 0. That can be very, very helpful in solving problems. Other things to notice is for an object that travels up, for a split second stops, and then comes back down, is the symmetry of motion. However long it takes for it to come up, if it comes back to the exact same altitude, to the exact same height, it'll take the exact same amount of time to come up as it does to come down. Whatever its initial velocity is as you launch it, if you launch it at 50 meters per second up, it'll slow down, slow down, slow down, stop. Then it will turn around, start coming down, faster, 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 and when it gets to that exact same height you launched it from, it'll be going 50 meters per second down, as long as we neglect air resistance. So we have symmetry of motion. We can use that to help us solve some of these problems. Let's take a look at an example. A ball thrown vertically upward reaches a maximum height of 30 meters. At its maximum height, what's the speed of the ball? Well, the object travels up. At its highest point it stops, comes back down. V equals 0 at its highest point. So what's the speed at its maximum height? 0. That simple. How about if we look at a basketball player who jumps straight up for a rebound? If she's in the air for 0.8 seconds, how high did she jump? All right, now we've got something that's a little bit more involved. First off, the basketball player starts on the ground, jumps up. So we're going to call up our positive y direction as we make our vertical motion table. Now we can also realize that the basketball player travels up and then comes back down. And at the highest point, velocity is 0. And if it takes 0.8 seconds for the entire trip up and down, it must take 0.4 seconds to go up and 0.4 seconds to come down. So here's another trick to solving some of these problems. Oftentimes it's a lot simpler to just solve half of the problem, which is what we'll do here. Let's analyze the motion of the basketball player on the way up only. Well, for a vertical motion table, we have v naught, v, delta y, a, and t. We don't know the initial velocity, but our final velocity, if we're looking at just the motion on the way up, we can say that that's 0. Acceleration, if we called up the positive direction, acceleration points down. So positive y is this way, acceleration is that way. They're in opposite directions. Therefore, the acceleration must be negative g, or negative 9.8 meters per second squared. And finally, if we're looking at just the motion on the way up, the time involved is 0.4 seconds, not 0.8 seconds. Got to be careful there. We're looking for delta y, how high she jumped, and we don't know v naught yet. Well, I know 3 things, so I know I can solve this problem. But if I'm looking for delta y, I don't see any equations that can give me delta y directly. So why don't we solve for v naught first, and then we'll find delta y. So we can start with v equals v naught plus at, or v naught equals v minus at. Now we can substitute in our values. V naught equals v, 0, minus a, which is negative 9.8 meters per second squared, times t, 0.4 seconds, for a total initial velocity of about 3.92 meters per second. So we know v naught now, it's no longer a question mark, it's 3.92 meters per second. Now we can solve for delta y. We can use any equation we want that has delta y in it, and the easiest one that I can think of, delta y equals v naught t plus 1/2 at squared. and we can substitute in directly. Delta y equals 3.92 meters per second times our time of 0.4 seconds plus 1/2 times a, negative 9.8 meters per second squared, times t squared, 0.4 seconds squared, for a total delta y of about 0.78 meters. That's a little less than 1 meter, about a yard, which makes sense. A reasonable vertical jump is somewhere in the 2 to 3 feet range. 3 feet's a really big jump, or 1 meter would be a really great vertical leap. So for a basketball player who's training, 78% of a meter, that's a pretty good jump. That's reasonable. So there's a problem where we had to go through a couple steps and also recognize the symmetry of motion as the basketball player jumped up and came back down. Let's take a look at one last sample problem. If we have a baseball player and she throws the ball upward with the speed of 30 meters per second, and we're going to neglect friction, find the maximum height reached by the baseball. Well, for this sort of problem, again, it's a vertical motion problem and the ball starts going up, so we'll call that positive y, and we can make our vertical motion table v naught, v, delta y, a, and t. Our acceleration points down, it always does, and since that's in the opposite direction of positive y, our acceleration is going to be negative 9.8 meters per second squared. What else do we know? It starts with an initial velocity of 30 meters per second. And 30 meters per second is upward in the same direction we called our positive y, so that's a positive v naught. We only have two things here so far. We're trying to find the maximum height, delta y. We need one more piece of information. Well, if the ball is going up and then coming back down, what we can do is we can realize that its highest point right there, its velocity is 0. So when its velocity is 0, that's at the point where it's at its maximum displacement. So if we want its maximum displacement, we'll solve for this problem when that final velocity is equal to 0. There's our third unknown. Right away, we can jump into our kinematic equations with those four variables. V squared equals V naught squared plus 2a delta y. Rearrange this to get delta y by itself. Delta y equals V squared minus V naught squared over 2a. Or delta y equals, as we substitute in with units, v squared, that's 0 squared, minus 30 meters per second, our v naught value squared, all over 2 times negative 9.8 meters per second squared. Run that through the calculator, and I should come up with a delta y right around 45.9 or 46 meters. All right, that should give you a good idea of what sorts of problems you're going to see. For next steps, why don't you see if you can create your own dropped object problem? See if you can figure out something interesting or fun to drop. Who knows, maybe you drop your physics teacher off the third floor roof of your school or whatever it happens to be. How long does it take that teacher to hit the ground? And then see if you can solve the problem. Then try your own vertically launched problem where you start with some initial velocity upward and see if you can solve that. And of course, if you need help, want more information or extra practice, you can always check out aplusphysics.com. Thanks and have a terrific day.